Okay, I guess let me get started. First, I'd like to start out by asking if there's any questions. Let's start to look at let's start with homework three. Have any people started on homework three? Couple people. Any questions or comments about homework three? Yes? I think I heard someone in TV land. No. Any questions or comments about homework three? Okay. Last class I also gave out the grad project. Any initial questions or discussion associated with the projects? What the rules are, what they mean? Um, again, I encourage people to start thinking about projects, and start playing with it a little bit so that when you make your project proposal, you know that it's something you can really do, that you've made enough progress on, that you know that there's going to be a happy ending. Any questions? Okay, let me try one other thing. Okay, last class I started talking about the probability distributions or statistical distributions. Um, and you know what I will say is the mother of all statistical distributions when it comes to analyzing data is the normal distribution, which we defined. And just to review, it is a kind of the classic bell-shaped curve. It's defined by a mean, completely defined by a mean and a variance. And because it's completely, or mean and standard deviation. And because and what's great about the normal distribution? Well, one, it is, it sort of fits a lot of different things. Things like height is normally distributed, sort of. Weight is normally distributed, sort of. Um, if you have to come up with, you see a bell-shaped curve, what's your initial reaction? Oh, that's probably a normal distribution. It's not always right, but that's a reasonable reaction. And one of the reasons why we found that so useful was it because the normal distribution is completely defined by its mean and standard deviation. Um, it has the property, well, it is, and it has the property that that you know exactly how much mass lies a certain number of standard deviations from the mean in a normal distribution. As we talked about it, roughly 2/3 of the points lie within one standard deviation of the mean. And when I say standard deviation of the mean, I mean I'm thinking in terms of z-score. Okay, if you take your value and you subtract the mean, divide it by sigma, that's going to give you your z. Z-scores of normally distributed data, 68% of it lies within one standard deviation. 95% of it lies between what you call it, two standard deviations. 99.7% of data lies within three standard deviations. Have anybody ever heard of the phrase Six Sigma? This was management guru talk for a while. What does Six Sigma mean? Does anybody know? Okay. Management gurus will say we want so much reliability in our organization that we know that bad things are only going to be Six Sigma events. Okay, something where the probability is so low that it doesn't matter. If you run an airline, how do you know you're running a decent airline? A plane crash should be a Six Sigma event. Okay, it should be very, very, there's some flights that go really well. Some flights go really badly. Okay, the worst kind of badly means the plane crashed, right? And you would like to think that the tail probabilities, what is the probability where a plane flight crashes? You would like that to be very, very low. And they aspire, I gather, to, sort of what you would be the tail probability of a normal distribution 6 standard deviations from the mean. Any questions about that? Okay, so normal distributions are good. Um, what's what's important to recognize is that not all bell-shaped curves are really firmly normally distributed. Note that the normal distribution is something that is a theoretical construct. There is a difference between probability and statistics. Probability is done by math theory guys on some level who are sitting there and making definitions and working out the consequences of it. Statisticians are the ones dealing with real world messy data. And there's a tension between them. When we see a bell-shaped curve, we normally think it is normal, but a lot of bell-shaped curves are not normal. One of the classic examples, which I gather I may have mentioned, but it's a good story anyway, is whenever there is a stock market crash, okay, you see a lot of hedge funds go bankrupt. And when they go back and dig, why did they go bankrupt? Often what they will discover is that what they modeled as a normal distribution was not really normal, okay? Stock returns, if you say what's the price of stock, what's the returns, essentially like the percentage change of a stock every day, okay? Sometimes, they're going to get taken over by someone with rich pockets, the stock jumps a lot. Sometimes, the CEO was caught embezzling all their money, the stock drops a lot. Sometimes there's normal changes with this thing. You can imagine a distribution of stock changes. And when you do that, it looks very much like a normal distribution. Okay, it looks bell-shaped. But one of the things that is true about stock returns is that rare events are more likely to happen, okay, occur more often than would be predicted by a normal distribution, okay? How many 10 feet tall people do you see? You don't see any because height is sort of normally distributed and it's rare to see something too many standard deviations from the mean. On the other hand, in a log normal distribution, you have fatter tails, and rare things are still rare, but they occur a lot more often than you might expect. So you can imagine this dialogue at a hedge fund after the crash. Why did we crash? Well, this thing, I didn't think this was going to happen. Why didn't you think it was going to happen? Well, it was 20 sigma away from the mean, okay? And then they said, well, but that's only if it was normally distributed. And the guy says, oh, well, and then everybody goes bankrupt together. Any questions about that? Okay. The other thing that is probably more common problem is that mixtures of populations is not normally distributed. When we look at what height is, okay, if you look at the distribution of height in the United States, I'm gathering this is what the graph shows, you see a bell-shaped curve, okay? It's not normally distributed. Why is height not normally distributed? Well, one reason is because the men and women have different average heights, and the population is a mixture of men and women. Okay? Does everybody agree? So when you look at the mixture here, the resulting thing looks sort of like a lumpy, looks sort of normal if you look at squint enough. But it should be clear that the mixture of a population of normally distributed populations is not normal. Any questions? Now let's look at this. Let's look at the height of men. Is the height of men in a population normally distributed? See people say, yeah. I'm going to say almost certainly not. One thing that's true about men is I guess men have kids, don't they? I was a kid at one point. If you take the fact that people are growing for the first 10 years, okay, that is not a kind of the normal distribution is kind of gathering a normal distribution is kind of saying, well, everyone's sort of like the mean. There's a little bit of a tweak here, a little bit of a tweak there, but there's a mixture. You've got populations of men and kids, okay? So let's eliminate the kids. Are men that are not kids normally distributed? Is the height of them normally distributed? Okay. No, why not? Give me some more. Why won't that population be normally distributed? Might depend upon what? Race or genetics. It could be. Does anybody belong to an ethnic group that they think of as being unusually tall or unusually short? I don't know if there is, but it's certainly true that some ethnic groups are historically shorter on average than some other. Certainly Europeans are taller than Americans. Now that may be genetics, that may be nurture, but certainly if we have a population of, a mixed population of people with mixed different genetics, okay, then yes, it's quite possible maybe every individual population looks normally distributed. But again, you've got a mixture there. Let's now take people who are all from India, okay, all male, okay, all from the same part of India. Are they normally distributed? Drop the kids, okay, all full height. Are they normally distributed? Now everybody says, no, it can't be, right? What else could be wrong? I'm going to imagine a certain part of the population got into accidents and lost their legs. Okay, you can kind of imagine that's a different thing that happens. It's a different kind of subpopulation. It's going to not be kind of governed by the same properties. Okay, the truth is that generally every population that you sample, okay, is not going to be completely 100% normally distributed in a theoretical Gauss-given way. Okay. But on the other hand, the normal distribution is still a great way to think about these things. If you're asking me to reason about height or IQ or anything else that I think grades, anything I think is going to be normally distributed, my first sense is to think, well, if it's normally distributed, what's the standard deviation? How many standard deviations from the mean are you? What does that make it? How rare is that? Okay? So any questions about that? The normal distribution is good to think about. Recognize in practice, it's an approximation to reality. But approximations to reality are still useful things. Anything about normal distributions? Okay, let me talk about another type of distribution that comes up a lot. That's actually quite interesting. Is sort of a distribution that models lifespans. Okay? Let's think of a process of trying to predict how long somebody's going to be alive. Okay? You can imagine that if you live to be, let's say 33,000 days long. 33,000 days is a pretty good lifespan, actually. Okay? How does somebody live to be exactly 32,000 years? Let's say I'll give you 33,000 days. How do you learn to live to be 33,000 days? Well, you've got to wake up 32,999 days and survive, right? And then on the 33,000th day, you've got to not wake up. Does everybody kind of agree? So you could imagine a process to govern what's the probability that I'm going to live to be exactly n days old. If you live in a world where there is a probability of dying, okay, of P on any given day, How do you live? What's the probability of living to exactly n days? For the first n minus 1 days, you've got to live. And on the nth day, you've got to die. Okay? If you live with probability p, you die with probability 1 minus p. Is everybody going to give that? And you can imagine that if we had the probability p of what you had of living each day, this would define a lifespan distribution, right? If I knew that everybody's chance of surviving for a day was 1 over 33,000, okay, then I could work out from this, what's the probability of living exactly a life of exactly n days? And it defines a lifespan distribution. Any questions about that? Now, we talked earlier about what if I have a light bulb that is rated to last on what's it called, 1,000 hours. Again, I'm used to buy, I don't know if you guys buy light bulbs these days. When I bought light bulbs, every light bulb had a average lifetime, and it might say 1,000 hours on it, right? If you wanted to model how long your lifespan, the light bulb was going to live, one possibility is every hour you flip the coin. This is what we did in when we're talking about the binomial coefficient distribution. Every hour you flip the coin to decide if it's going to live or not. If the coin came up heads 1 out of every 1,000 times, you would be able to figure out what's the probability of burning out? How many burnouts would you have after 10,000 hours? So it's not quite the same thing as knowing how long what the distribution of lifespans in the bulbs are. What we're interested here is what is the distribution of runs between the heads when the light bulb's burned out? Any questions? Okay. This distribution of lifespans is governed by something called the Poisson distribution. Okay? And the Poisson distribution kind of takes the limit of what I had, and it says the probability of living exactly X days is, okay, e to the minus mu is the mean, okay, times mu to the x, the mean raised to the days, divided by x factorial. Where does this come from? Not going to tell you. You probably saw that in a probability class, actually. But what's the meaning of this thing? First of all, notice that in the Poisson distribution, the parameter here was mu. X is what you're asking about. The thing E, everyone knows what E is, 2.718, ... Mu was the mean of the distribution. Poisson distributions are completely characterized by the mean. Remember, we had the normal distribution. What was the normal distribution characterized by? The mean and the sigma, right? In some sense, if all you have is a mean, a Poisson distribution will, make a guess as to what the entire distribution is. Okay? Now, of course, a uniform distribution could also make a guess. Whether it's a meaningful guess, it depends upon the application, right? But it's interesting because we defined the Poisson distribution in terms of this probability of dying per day, okay? You probably don't know what the probability of dying per day is as a human being. But what's the average lifespan in the United States? What's the average lifespan in the United States? What'd you say? 76, 77, right? So knowing the mean is a relatively easy thing to know, right? You don't have to make any assumptions about the distribution or anything like that. The thing to see here is that for any given P is going to define a distinct mean of the Poisson distribution. Why is it? What's the mean lifespan? It is going to be the sum over all possible lifespans k of k times the probability of living a life of exactly k, right? And this formula told you the probability of living a lifespan of exactly k, right? So in some sense, the formula is defined in terms of p. Every p is going to define a distinct value of mu, okay? And so in some sense, the nice thing about the Poisson distribution is that it reduces needing to know the daily probability of dying from to a mean, which is something that's easily observed in the population. Any questions? Any questions about how the Poisson distribution can have only one parameter, okay, and yet define something that sounds meaningful here? Yes?
This we suppose that the events are independent.
Yes. This assumes that the events are independent each day. Okay? So in other words, your chance of dying on, actually what it means is actually your chance of dying on day I. First of all, it depends on you having lived up to day I, right? But this says that your probability of dying on any given day you're alive is the same. That is the assumption of the Poisson distribution. Does that answer what you wanted to know? Okay, any questions? So how well does it work? Okay, well, you said that everybody lives to be 77. I'm going to give you guys 3 more years. Okay, let's say that the average lifespan was 80. Okay, now what does the Poisson distribution look like? This is a figure I made yesterday. Okay, I got into my Poisson distribution calculator and just added that one parameter lambda. What does it look like? Well, according to this, sizable number of people did not start, visible number of people, this is the probability of dying, living to that year. At the peak year of about 80, it looks like about 4 or 5% of the people live to be exactly 80 by this model. Okay? It looks like visible people don't start dying. You don't start seeing visible amounts of dying until it looks like about 55. Hold on. Let's go back there. I'm sitting about here. So you see that there's a chance you won't see me tomorrow, but it's still pretty low. Does everybody kind of agree? Okay. According to this, what does it show? It shows that there are people that go on. It says normal lifespans are up to about 60 to, let's say, maybe up to about 104, 105. That's kind of what I'm seeing here, right? Is this reasonable? What do people think? Is this a good fit or a bad fit to what your conception of the world is? You say bad? In what way is it bad?
Independent, and I don't think the life independent every day.
Okay, so now he's asking something a little bit different. Okay, so I'm saying, does this distribution look bad? And he's refusing to look at the distribution, which is fine. He's instead questioning the model. He's saying, according to this model, everybody has, at any age, you have the same probability of dying. That's kind of what I think you're asking about, right? Do we think that's true? In what way do you think it's different? How does the daily probability change of dying as you age? Okay, so you think that the daily probability, that if I am 101, my chance of dying tomorrow is greater than it is when I'm 23. That's kind of what you're sort of assuming. Okay? And that's not unreasonable. Okay, that's probably a fair statement. Okay, which would argue that to do this completely right, you probably need a better model. Okay? Does everybody kind of agree with that? But that's still the first question is, how good are the predictions if we assume everybody died the same day? Had the same probability of dying each day.
And other regions might have different.
Okay, you're saying you don't think you're saying, well, other countries have different chances of dying.
Yeah.
Well, we agree that if you go to a place that has an average lifespan of 50, okay, there are countries where that sadly is true. Then what would that distribution look like? It wouldn't look like this. Well, you guys, again, you guys are in America now. Let's leave this let's say that the lifespan was 80. That's kind of the number that we were given. Given that the lifespan is 80, do people think this distribution looks reasonable or not? That's kind of, I guess, the question, right? Remember, the Poisson distribution is supposed to be a model, okay? All you knew walking in here, you told me that we had this country with a lifespan of 80, right? An average lifespan of 80. You didn't give me a standard deviation. You could imagine that there is a country who's at 8 has a lifespan of 80, who bloop, everybody dies on exactly their 80th birthday, right? Actually, I think when my daughter was growing up, she was reading these fiction novels, and there's these dystopian things where they poison everybody on their 80th birthday. Which one was that? Divergent or something like that? Does anyone? Anyway, you could imagine a country where they poison everybody on the 80th birthday, right? Great healthcare system till you take the wrong meal, right? That would have a mean of 80. You could imagine a world where people live uniformly from 0 to 160. Okay? That would have a mean lifespan of 80, right? Now, compared to those distributions, this one I think looks pretty good, doesn't it? Okay? It gives you a little bit of an insight. It tells me that I'm reaching an age where people start to die, right? I am telling me that it is very unlikely people live to be 120 or something like that, 110. So this model isn't terrible. That's, I guess, my reaction to this model is not terrible. Is the model perfect? The answer is no. Okay? And actually, as to the question of the assumption of the model, it's fair to assume, the question of is the probability that you die on every given day constant? It's a lot flatter than you would think it is. Okay? If you looked at it in a world where, notice that in a world where here everybody is dying, has a day of dying, the probability of dying on any given day is constant. The probability of dying is low enough that most of the population, lives to be a quite reasonable age, while not living to too excessive an age. Okay? When demographers try to look at the question you're asking, is there an increased rate of dying as you get older, per day basis? The answer is yes, but it's not as wildly higher as you would think it is. It's not that grandpa has a much greater chance of dying tomorrow because he's 80 and you're only 20. It's a little bit higher. But it's more the accumulation of, that your chances of dying on any given day is, it's the fact that you've got a Poisson distribution that governs most of it. Any questions? And you can push back if you wish. I remember reading a study about people who live to be 100. And it seems, again, there's not a lot of data on people who live to be 100. Why is that? because there are not that many people who live to be 100, right? But we're interested in them because we would like to be like those people, right? And one thing that they try to study is how does the rate at which people, the probability of dying in each day, change as you get older. And I remember seeing a paper that suggested that it didn't change once you got to a certain point. By the time you were 100 or so, your chances of dying tomorrow are the same as the guy who's 110. Okay? If I am to remember the study, this half-remembered study properly. Okay? So the moral here that I'd like to say is the Poisson distribution does, to my mind, an admirable job of fitting this. Okay? Not a perfect, okay? But an admirable job using a very simple assumption. Any question about that? I got a picture of what is supposed to be the observed lifespan distribution. That's what I got down here. What does it look like? I don't know how well you can see it from where you are. But according to this, if you look at it, does it look like a Poisson distribution? Not really. But what's big differences? Notice, first of all, there is a large rate of infant mortality. Okay, that's not explained by the Poisson distribution. Okay, unfortunately, a lot of children die in their first year. Okay, once you make it past the first 10 years or so, then you've got it. Note that there is a long tail here. Probably that long tail is not people getting sick and dying. Probably a lot of that is people, driving cars into walls and doing drug overdoses and things like that, right? When you look at the distribution in practice, it is a little bit skewed. Okay, it's not the median is not at the center the way it would be with a Poisson distribution. Okay, and it does look like there is an increased rate of dying. Okay, once you get to a certain point. Okay, but all in all, I don't think the Poisson distribution did a terrible job. And I like the fact that it's one parameter and we can reason about things interestingly. Any questions? Any questions in TV land, by the way? I know I've seemingly forgotten from you guys and not hearing from you guys. Another example of where I have a mean but don't have a distribution in life is how many kids does the average family have? Okay? When I was growing up, okay, the factoid that everyone knew was that the average American family had 2.2 kids. Okay? Now it's actually lower than that now, a little bit. But let's go with that. If the phenomena of deciding how many kids a family had was governed by, the two people sit down and say, should we have a kid? And they say, yeah, okay. After they have a kid, should we have another kid? Yeah, okay. Should we have another kid? Hell no, right? You can imagine a situation like that. If they make that distribution, that decision with some probability P, okay, then you would expect that it'd be a Poisson distribution, okay, that would govern how many families have how many kids, okay. And in the book, I tried to find some data on that and fitted it, and I was amazed by how well the tail fit. That the number of families with 9 kids, 8 kids, 7 kids, 6 kids were about what you would expect there to be. Okay? So again, a simple model just starting from a mean. If you assume a Poisson distribution, and that's a reasonable model in this case, that's enough to give you kind of a distribution that makes some sense. Any questions about Poisson distributions? Okay. The last distribution I want to talk about is one that is these days, comes up a lot in the kind of things that computer science people like to do. It's funny, people didn't talk about this distribution very much, 30 years ago. But kind of the way the world has emerged, suddenly power law distributions are kind of recognized as something that lurks behind a lot of different phenomena. What is a power law distribution? A power law distribution says that the probability of getting the random variable value of x is equal to c times x to the minus a. Okay? So c is a constant. X is the value we're interested in. And a is the main parameter of the power law. It is an exponential, right? Let's say, as is typically the case, a equals 1. Let's say the most common case might be a equals 1. Okay? What does this mean? Okay? As x grows bigger and bigger, what happens to the probability of x? It goes down. Does everybody see that? C is a constant, x to the minus a, assuming you've got x as a positive number, okay? Then it says that the probability of getting x, okay, goes down as x gets larger, right? It goes down exponentially, which would argue that it probably goes down pretty fast, okay? Thinking about it, let's think about income. Income, what the probability of making $100,000 a year is reasonable. Probability of making 200,000, fewer people do that. 400,000, 800,000, such and such. But there are people who make many, many billions of dollars a year. In a power law, the probability of making large numbers goes down. It gets rare, but it doesn't get unbelievably rare. The idea of being many standard deviations from the mean is the probability of that is much higher in a power law than it is in a normal distribution. Okay? In fact, what's interesting about power laws is the values do not really cluster around the mean. Instead, you have larger and larger values getting rarer and rarer, but kind of the value never going away. Okay? Any questions? When you define what you would call like an 80-20 rule, often you will say 20% of the people have 80% of the wealth in the United States. Does everybody agree with that? You may not agree. It may be that 10% of the people have 95% of the wealth. But whenever you have a rule like that that's consistently applied, that is kind of what lies underneath a power law distribution. Any questions? So let's look at an example of a power law distribution. Populations of cities. Okay, many of you are aware of cities. Okay, you're aware we live near Manhattan, New York City, right? New York City is the biggest city in the United States. Okay, although dwarfed by many other cities around the world, apparently. I took a look at a data set of what are considered to be cities in the United States. Remember, at some point, Stony Brook stops. Stony Brook isn't a city. Stony Brook may be a town. It's kind of a. So you can imagine that there's a threshold by which you say a city is. Maybe a city has 100,000 people in it. When you take a look at all U.S. cities, the data on it, the average U.S. city has a population of 165,000. Okay? When you take a look at that data set, if you compute the standard deviation of population of cities in the United States was 400,000. Let's stop and take a look at that. Does that seem weird? Okay. The standard deviation here is very, very large relative to the mean. Does everybody see that? Is that possible? Of course it's possible. Okay. But it does tell me that the guarantees on shapes, and this isn't what we think of as a normal distribution. This isn't the way we're used to thinking about things work. But let's think about it. Even if we had a mean of this and a standard deviation of this, if we assume cities were normally distributed, we know that 67% of the cities should be within plus or minus one standard deviation, right? So that would argue that that 67% of the cities would be within 165 plus 410 to 165 minus 410. We would think that 95% of them would be within two standard deviations. You would expect that 99.7% of them would be in three standard deviations. Well, there's only about 100-ish or 200-ish cities in the United States by this measure. Okay? If you assume that there was a normal distribution on city populations, you would expect that the largest city in the United States should be about the size of Indianapolis. Okay? So if cities had a mean and there was a natural bell-shaped curve fluctuation about it, the biggest city in the United States should be Indianapolis. New York City has 8 million people. Why does New York City have 8 million people? Okay? It isn't that all cities are alike and that there's some that are a little better and some that are a little worse and that they have a normal distribution like height. Why is it that New York City is so big? Okay?
People are more likely to move there than to.
You're saying because, what you call it? Okay, you're saying because there's already a lot of people in New York. More people, a disproportionate number of people want to move to New York to be like those people, right? Is there anyone here who's dreamed of living in New York? One person, a few people. You should. New York's the greatest place in the world, I will tell you. That's not a math thing, that's a personal thing. Okay? But if, in fact, cities attract population disproportionately because of how big they are, it's a rich get richer phenomena. Okay? And as a rich get richer phenomena, you would expect that the bigger cities would grow and keep growing disproportionately. Okay? And that defines a power law thing. In real life, do the rich get richer? Is the next dollar more likely to go to Bill Gates than it is to me? Darn right. Okay, now why is that? Okay, well, first of all, if they just put it in the bank, if you put your money in a savings account, invest it, it's going to grow 8% a year, right? When Bill Gates' money grows 8% a year, that's an extra 8 billion or 10 billion a year. When you put your money in the bank at 8%, that's an extra $2 or $3, right? Okay? So recognize that that's part of it. There may be other possibilities. If you're a brilliant investment advisor eager to give advice, do you call Skeena or do you call Bill Gates? Certainly he has more people knocking on his door. He has the best people knocking on his door, right? So mechanisms like that explain why power laws happen. Now, Jimmy is asking on the thing, is the wealth of people in the world a power law, or is it normally distributed? Now let's start to think about what the implication of it is. If it was normally distributed, what do we think it would look like? You would expect that there would be a mean, wealth, which is probably not that large in any particular in the world. What's the mean wealth in the world? I'm going to guess the average person has, and I'm being optimistic here, actually over the entire world, if you measure wealth as much what they actually own, what would someone guess the average wealth is? I am going to guess $1,000 or less. Okay? So if in fact the mean wealth is $1,000, okay, then do we think it's normally distributed? Certainly not. What do we think is it? Are there people, a lot of people, more people who have $1,000 or more people who have nothing? I think most people would think it probably has nothing. I'm going to guess the distribution looks something like that. This is the frequency. This is dollars. There's 1,000. My guess is you have the peak of the distribution probably occurs with zero wealth, right? Actually, if we count bills that people owe as being negative, I was going to say nobody can have less than zero wealth, but I expect that unfortunately that's probably true, not true. There probably are people who have slightly negative wealth, right? But the important point is that there's people who have 1,000, are there people who have 10,000? Are there people who have 1,000,000, 10 million, 100 million, a billion, 10 billion, 100 billion? You see, we're still saying yes. What do you think the standard deviation of the world's wealth is? What do you think the standard deviation of the world's wealth is? Remember, you've got to have the case that a lot of the probability has to lie within 2 standard deviations of the mean, right? For any distribution. What do you think the standard deviation of the world's wealth is going to be? If you need that, let's say you need three-quarters of the people to lie within 2 standard deviations of the mean. If the mean wealth was 1,000, what do you think the standard deviation is? People see what I'm asking? World wealth, we've agreed the mean is about 1,000. We know based on first class, I think in here, or one of the first classes, that 75% of the mass has to lie within 2 standard deviations of the mean. What is the standard deviation of wealth? You say 50,000? You think 75% of the people in the world have $60,000 or less? 51,000 or less? I would guess it's probably a lot less than that, actually, when you talk about the world. But let's go with it. Let's say that the standard deviation was, what did you say? You said that the 75% of the people, the cutoff was 50,000. That would mean 2 standard deviations from 1,000. A standard deviation was 25,000, right? If sigma equals 25K, how many sigma from the mean is Jeff Bezos? He has 100 billion. This is an important point. How many billion? 100. That's 100,000. It's 100 million. That's 100 billion. How many 25,000s are there in 100 billion? 400,000. Jeff Bezos is 400,000 standard deviations in wealth from the world average. On television, is the wealth of people in the world normally distributed? Absolutely not. It can't be, right? Instead, it is something like power law distributed, where as you double the wealth, okay, you get a fraction of people have that, but half of a certain number of people is still a certain number of people, okay? And that is what the situation is, okay? Any questions? That is what makes power laws interesting. They really look a lot different than normal distributions. Any questions? And the reason for that, just to emphasize again for the question on television, it's the fact that power laws are interesting. The 80-20 rule, it's not just that if you take the people in the world, okay, and you say 20% of them have 80% of the wealth, it's that that rule holds at all different scales. Let's say you take the billionaires, okay, are there rich billionaires and poor billionaires? Yes, okay. You can imagine the shame of I'm going to guess, normal run-of-the-mill billionaire when they're in a room with Jeff Bezos, right? What is the situation if you get the billionaires together? I'm going to claim that 20% of all billionaires have 80% of all the money owned by billionaires. Okay? The fact is that these 80-20 rules are kind of, in power laws, hold at all scales. Sometimes people call power laws scale-free distributions because they look the same when you zoom them up. If you took a look at just the billionaires, the distribution would look the same on a graph. The shape would be the same as if you look at all the people, as if you look at everyone above 10,000 or 100,000 or a million. Okay? Any questions? So this is why power laws are interesting. Okay? And I think we've had a good discussion about that. Any questions? Again, let's look back at the city population power law. Okay? This here, when I had the data, was a population of, I took all the cities, I sorted them from the most, okay, to the least population. Okay? The x-axis is their rank in the population, from biggest to looks like 300th. Okay? According to this, there were 300 cities in the United States. The y-axis was population. Okay? What do you see on this graph? Can anybody tell me anything interesting about that graph? Okay. Where is New York City? Does anybody see New York City? New York City is not on that graph. Why is New York City not on that graph? You see I got some white over here? In order for you to hope to see something, I deleted all of the biggest cities in the country. It may have been the top 10 cities in the country. I left Indianapolis size city was here. Does everybody see that? Where would New York City be on the scale of this graph? This is 600,000. This up here would be 800,000. This here would be 1.6 million. Up at the very top of the slide is about 2.5 million, right? It's going to go, the New York City is out there. Does everybody see it? Okay. What if I plotted New York City on the map? What would it look like if I showed just the cities, just New York, where I did show all the cities, and I scaled it to a size that people could see? What would it look like? New York City would be 800 million, 8 million there. Maybe Chicago would be 3 million there. Maybe LA that would be LA. Maybe Chicago is here. And everything else is just scum on the line. Does everybody kind of see that? You couldn't make a sensible plot of all the cities and the population of all the cities by rank because there is such a difference, because there's a power law distribution. Any questions? What you could do, however, is do a log-log plot. What if we plot the log of the population versus the log of the rank? Okay? Then I can tell you where New York City is. That's where the missing cities would be. I should have had them on this graph. But one of the interesting properties, in fact, the defining property of a power law graph, is if you do a log-log plot of the values by rank, you end up getting a straight line. Okay? So straight lines on a log-log plot are kind of what smells of a power law. Any questions about that? Okay? And again, when I say that there is a 80-20 type rule, when I made this slide, Bill Gates had 80 billion. What does he have now? I haven't done any recent checks. It certainly went up, and he got divorced. It probably went down. Okay? But what is still the point? If Bill Gates was the richest person in the world, what is the distribution of wealth among billionaires? If we have the property that Bill Gates has twice as much money as 5 hyper-billionaires, who have twice as much money as the 25, 20 billionaires, who have twice as much money of 125 multi-billionaires, who have twice as much money as 625 garden variety billionaires. Does everybody kind of see what's happening here? If this was the distribution, the number of people with a population got divided by y. Here y was equal to 5. Every time you multiplied the population by x equals 2. If you have a world where every time you multiply the value by x, you divide the number of people by y, that is a power law. Any questions? So again, let's look at the probability distribution governing power laws. And now that we have an idea what they are, maybe it makes more sense because it's a little bit weird looking at first. We say the probability that you have a value of x, okay, x dollars, okay, is some constant times x to the minus a, okay? Now, c is just a constant that we're gonna not care about. It's going to be, we need a constant there because we need the sum of these probabilities to add up to 1, right? Remember, whenever you consider a random variable and the probability of each value there, the sum of them have to add up to 1. If they add up to 963, if you divide every number by 963, it adds up to 1. That's what the role of the constant is. Okay? But the more important thing is look at the implication of what happens for the given a. That a is defining the slope of the plot, the line on the log-log plot. Okay? What happens when you double x? How does the probability of this to x compare to the probability for a value twice as big, 2x? What happens? That would be c times 2x to the minus a. Does everybody agree? If this expression was what we were using, if this was the probability of x, what would be the probability of a value twice as big, 2x? It would be c to the 2x minus raised to the minus a. What is this? This is equal to c times 2 to the minus a, okay, hold on, times x to the minus a. Does everybody see what has happened? Whenever we doubled the value of x, okay, we reduce the probability by this value of 2 to the minus a. So just like I was saying with that 80-20 rule, right? Every time you double the amount, you reduce the probability by 2 to the A. Okay? And so there is kind of a steady thing. Bigger values get less and less probable, but they still don't have zero probability. Okay? And it doesn't go down that fast. Any questions? Oh, okay, on television. Okay? Okay. Jimmy, can you say something? Because you have a long thing for me to read.
Yeah, Professor. So my question again comes back to the wealth. So it seems like, if you take into consideration the depth of people, there are people who have considerable debt, right?
Okay?
So yeah, so we will have a power law distribution like with some people towards the negative side of the wealth scale, right? So sort of we will
Okay.
have mirrored power law.
Okay, so now what you're saying is real world wealth, you're saying doesn't start at zero because of debt.
Yeah.
And I think I agree with that. Okay? So, but let's now think about what is the distribution of wealth among people that have less than zero. If this is zero wealth, what is the you tell me, let's walk through it and look at the shape of it. What do you think the shape of people who have negative wealth is? Okay? I'm going to guess that probably people with negative wealth, most of them have relatively small negative wealth. Their net wealth is negative 100, negative $200, not negative $1 million. Why is that? Because if you have zero wealth, it's probably hard to get someone to loan you $1 million, right? I mean, does this seem reasonable to you? I would imagine the negative part of the distribution, almost all of that people probably have, there's a non-trivial number of people with negative wealth, but they're probably on average not that negative just because they never had the chance to borrow money. Okay? Now, there's probably a few people, maybe Donald Trump is over here actually. Okay? Some people think he's in the red. Okay? Because he borrows a lot of money as a real estate guy, right? In China, there's this guy who has Evergrande, I think I've been reading in the newspaper about, right? There's this property developer that's going under there. He's got serious negative wealth now, and he's in trouble, right? But there are very, very few of these people, okay? I'm going to argue that negative wealth is probably a different phenomena than real wealth, okay? And that you might there's still going to be a few outliers of failed billionaires, okay, who have tremendous amounts. But it's a different phenomena. And I'm going to argue that negative wealth is probably a less interesting phenomena than than you know than negative than the power law of income. There's a question on here: is the power law a mixture of different normal populations? And the answer there is no. Okay, you could imagine maybe they would tell you that you could think what governs different population. Maybe it's the case that 90% of people are normal schlubs, and normal schlubs have a wealth that's normally distributed, and there's 9% of the population that are super, are stars, and stars have a distribution that looks like this. And maybe you're imagining that there's 1% of the population that are hyper geniuses, and it looks like that. No, you don't have the world organized like that. Okay? I don't think the world is organized as tiers of people, each of which in that population, they behave with kind of a natural variance in distribution like a normal thing. Okay? The power law is a different phenomena. It's a phenomena of there being a mechanism by which rich get richer. Okay? Any questions? Okay? Any other questions in TV land, especially by oral? Okay? So it's important to recognize that a power law is a quite different beast than a what you call it? Than a than what you would expect from kind of normal random variation. Okay? A lot of things we see in the world, when you plot them on a log-log plot, show a straight line. That is a sign of them being a power law distribution. Okay? One of the classic examples, the one that makes computer scientists think about this, has to do with phenomena on the internet. Suppose you drew a graph, a network, where every website in the country was in the world was a node, and you have links. Every web page links to other web pages. Okay, you might be interested in, for every page on the web page in the world, there are a certain number of links to it. Some pages have 0 links to it. Some have 1 link to it. Some have 2 links to it. Some have probably many, many, many millions of links to it. What's a website that has many millions of links to it? Probably Google, right? A lot of people's page will say search box linked to Google, right? So what is the story there? Why is it that everybody links to Google? Okay. Well, if you're going to link to a search engine, which search engine are you going to link to? You could link to DuckDuckGo, right? Are people more likely to link to DuckDuckGo or to Google? And why are they going to link to Google? Is it because Google is better than DuckDuckGo? I don't know. I don't never use DuckDuckGo. I go to Google because Google is the biggest, okay? Probably it's the biggest because it's good. But at some point, these things become self-reinforcing. People use Google because people use Google. Because a lot of people use Google, Google has a lot of data and can make their search engine better, right? And now that their search engine is improving faster than DuckDuckGo, are more people going to probably use Google? The rich get richer. That's a phenomena that defines a power law. And sure enough, when you look at, one of these things, here's the internet one. Okay? Okay? It displays the degree is a power law. Okay? There's other things that are power law distributed that people don't know about. Earthquakes. What is an earthquake? Okay, do I have that on the graph? I can't find my earthquake graph. The frequency of which you have an earthquake at a certain value on a Richter scale is defined by a power law. Has anybody ever been through an earthquake here? Okay, does anyone remember what the power law, the value on the Richter scale your earthquake was? 5.2 or something like that. Anybody else? Anyone better than 5.2? 6.4. Okay, so we got a 5.2, a 6.4. Okay. Now, she is saying, well, that's not so impressive. It's only one bigger than mine. But actually, Richter scale is kind of an exponential type scale, right? When you go to the toilet, that's like 0.1, that's like 1 on the Richter scale. Okay? The thing that the flush makes, okay? The point being that the power doubles, okay, or goes up by, maybe it's a power of 10 or so every point, okay? What does the distribution of earthquakes on a Richter scale look like? It turns out it seems to be like a power law. There are 10 times as many earthquakes of scale 5 as there are of scale 6 for some value of 10. Okay? There are 10 times as many earthquakes of size 7 as there are of size 8. 10 times as many of size 8 as of size 9. Okay? That is what a power law means. And what does that mean? It's not like, oh, I've lived through an earthquake. I know all earthquakes have power that's roughly about the same. I know what earthquakes are like. There is going to be an earthquake 10 times, 100 times, 1,000 times more powerful than what you had. They just become rarer and rarer. Okay? And that is what, if there's a power law distribution on earthquakes, that's what happens. Any questions? Okay. Now, probably the most important power law that people encounter is something called Zipf's law. What is Zipf's law? Zipf's law is the power law that it was kind of discovered by a guy named Zipf, okay, to explain word frequency use in language. Okay? What did Zipf learn? In English, what's the most popular word? The. Okay? Now, what is the second most popular word in English? I don't know, but let's say sounds like a good guess. According to Zipf's law, the second most popular word should occur half as often as the most popular word. The third most popular word should occur 1/3 as often as the most popular word. Okay? And this is actually a graph of the x-axis is rank from 1 to 100 for the 100 most popular words in Wikipedia. This is showing how many times did it occur. Actually, according to this, it looks like of was the second most popular word in Wikipedia. Okay? You can imagine a distribution like that. The most popular word was the. According to Zipf's law, the second most popular word would occur 1/2, third 1/3. In general, the kth most popular word occurs 1/k as often as the most popular word. Okay? This defines a power law with that exponent 1. Okay, so remember we talked about the power law. We had this power laws were defined in terms of this exponent a. If the a is -1, okay, then we've got a Zipfian distribution. Okay, and so if you have a power law, kind of, the first assumption or first way to think about it might be to assume a is equal to 1, and Zipf's law holds. And there's all kinds of interesting implications of this. Okay? A lot of things, when you look at them, how many times is it used as a function of rank? Okay? That is probably governed by a Zipf's type distribution. I write books, okay? I look on Amazon. I don't know if you guys noticed, but does everybody see that on Amazon, whenever you look at a page for a book, it'll tell you where it ranks on its bestseller list? Okay? On a good day, my algorithms book will rank 30,000. Unfortunately, not all days are good. But if I have a 30,000, if my book ranks 30,000th on the Amazon bestseller list, what fraction, if there's a Zipf's distribution about it, what fraction is it that I sell compared to Stephen King, the #1 book on the list? I probably sell about 1/30,000th as many copies as he does, right? And how do I compare to someone if I got my rank to 15,000th from 30,000th? How many more copies would I sell? I would double my number of copies sold, right? Okay? The interesting thing is a lot of things are governed by the Zipf's distribution. You have the intuition of that from word frequencies, and that is a power law. Okay? Any questions about power laws or Zipf's distributions or anything like that? Okay? I've got 5 minutes and I don't want to start something new. Is there anybody can ask any question to stall me for just a minute or two? Any questions about homework or anything like that? Somebody. Yes.
So if we have to submit a project proposal, right?
Yes.
So for that, if you're not satisfied with one, you have to can we submit more than one?
Okay, so the answer is about project proposals. The question is, can you submit more than one project proposal? And the answer to that is no. Okay, the reason I want you to submit a project proposal is I want you to show what you're going to do. If you're going to tell me, oh, I'm going to do this or this, two wildly different projects, that is bad. Okay, so it's clearly got to be one of the projects. Your proposal has to map to one of the projects that I give you. Okay, now within it, there are different directions you can go, right? And ideally, your proposal will say, I think what I think is we're kind of most interested in is this part of the project. We started playing around with it, and I can get data for this, and I can do this. This aspect of if you pick the fantasy football thing, trying to figure out how good or bad people are at putting together fantasy teams. That sounds like an interesting question. That might be different than somebody else ends up getting into. Okay, but no, I need you to have one project proposal for one of these projects. Okay, ideally drilling in a little bit about what the directions you want to go in. Any questions? Okay, if not at this point, if there's no questions, I'll let you go now. Okay, I've kept you over for 3 minutes before, so call it a wash. Okay, thank you very much. Next class, we're going to talk about statistical significance testing, and that'll conclude our unit on statistics. Okay, thank you.